So what we're looking at is a spectrum image data set, so STEM EELS data acquired from a fib section that was cut from a solid oxide fuel cell sample. So on the left-hand side, we have yttria stabilized zirconia, and on the right-hand side, ceria, or kind of doped ceria. So this is the survey image, and then the spectrum image data was acquired from this region that we see here. So I'm actually only interested in kind of extracting some chemical information perpendicular to this interface. So something that would be nice to do is, instead of having kind of the 3D data set, it would be useful if we could have some way of summing or binning in this axis that's parallel to this interface. So a really nice way to do that, I'll show you. So we, first of all, we use a line profile tool. So right click, line profile on the spectrum image data. And then let's draw a line profile from the substrate into the ceria. So one thing, remember, if you want to constrain this line to be parallel to one of the image axes, a nice way to do that is to hold the shift key on the keyboard. So now that line can only be parallel or kind of at 45 degrees to one of the sides of the image. So I'll draw my line profile out there. Then the next thing we want to do is increase the integration width of the line profile. So hold the plus key, or shift plus, and then let's move it down slightly. So it's going to expand from the center of that line. Let's do a little bit more. Okay, I'm happy with that. Next, move the cursor to the edge of this line, the right click, and then you have this menu item that says extract line scan SI. So I'm going to do that and then rearrange the data a little bit. So let's resize this one, put that one there, and then, yeah, that looks good. So let's, oh yeah, right. So you can see already from the data set, we can see the ionization edge that we're interested in. So we're going to kind of focus on this guy here, which is the cerium M45 edge. So one thing that's important here, so when you kind of do this extract line profile from SI, you need to kind of be aware that it's going to go from the beginning of the line to the end of the line. So because I started my line profile in the YSZ layer, the YSZ is kind of at the lower pixel indices here. So it starts off YSZ and it comes down to ceria. So if I drew the line the other way around, this would be inverted. So we'd be starting in the ceria and we'd be going into the YSZ. So just pay attention to which way you draw your line if you use that function. Another way to kind of just be really sure, we can use the picker tool, extract spectrum. So I'm going to put that down here. And then as kind of you've seen before, so if you go select the spectrum image, SI, and then mirror extraction ROIs. So let's try that out. So now we can actually mirror where this spectrum is extracted from. So this is showing me where we are in this kind of line profile that I drew. Also shows you where you are on this intensity profile. You can move around. You can change the integration width. You can, that's kind of a nice thing to get into the habit of using because it's really clear what's going on. So you can see, we can see the M45 edge there. Oxygen. And then if you go in back in here, we can see that we've got zirconium, oxygen there. Okay, but we want to focus on this guy here, and we're doing non-linearly squares fitting. So let's kind of move along with that. So I'm going to zoom in some, and then let's do the fitting. So the first thing that we need to do is go into a technique where we have the fit stuff. So let's go to the analytical technique in data analysis. And then you want to, if your palette isn't already expanded, you want to kind of expand your least squares fitting. And then we're going to be in the non-linear least squares here. So NLLS. Okay, so we're going to start with a fitting. So first of all, we want to kind of take care of the background. So instead of removing the background, we can actually have the background as one of the fit components. So I'm going to draw an ROI here. Go up to the Add an LS Fit Model button. And then if we click there, then we get the option of all these different kind of fit models, which we've seen. So previously we focused, I think, mostly on Gaussian. So we're going to move on to some of the other ones. So, okay, so we all know that power law is kind of the best model for backgrounds if possible. So we're going to go power law. And let's see if that looks okay. So obviously it diverges here because of the oxygen edge, but kind of in this region and then kind of out to high energy loss, that looks to me to be a good fit. Okay, so now we need to take care of the actual ionization edge itself. So it has kind of 2, 3-ish kind of components that we're going to deal with one at a time. So the first thing we're going to take care of is the basic edge shape, and that's where this kind of hybridized method kind of comes in. So I actually want to use this one here that says reference, but we need a reference to add in. So the reference that we're going to use is going to be the Hartree-Slater cross-section shape for the Cerium M45 edge. So there's a neat feature in the software. If we go up to the eels menu, let's first of all make sure that you have the spectrum selected. So I'm going to click here. So we go to the eels menu and then compute cross-section. So if we click on compute cross-section, it brings up the compute cross-section dialog, and this allows us to plot a cross-section for an edge that we are interested in. So first of all, I already have Cerium M here selected. So first of all, we want to select Cerium from the periodic table. So we're going to go into the periodic table, select Cerium. Okay. Don't need to change the calibration units or the chemical shift. What we do want, though, is we want experimental conditions and energy range to match this data. So we could type that in manually if we wanted in these fields, but we can also just use this one, which copies the conditions from the frontmost eels data set. So that's why it was important to make sure that this was selected. So I can click that one, which imports the beam energy and the collection and convergence angles. We can also do the same here with energy range. So let's click that and it will match the start and end energy and the dispersion and the number of channels. So one thing to be a bit careful of is to always just verify that your angles are correct. So I can see here that this doesn't look quite right for a STEM data set. So the convergence semi-angle is 0 and the collection semi-angle is 100. So convergence semi-angle is 0 probably means that that was, well, it would imply that it's TEM data because it would be parallel. But we can see that it's a STEM data set. And so probably what's happened here is just this is old data and that metadata wasn't properly populated at the time. So I'm just going to go ahead and kind of arbitrarily change that to some typical parameters that I usually use for STEM. So we go 20 and I'm going to just put in a collection angle of 40 just for demonstration. Hit compute. And now we have this cross-section shape for the M45 edge for Cerium in this new image window, which on my system is called H. Okay, so the next thing, now we have that reference, we want to go back to the spectrum that we're fitting to. So this extracted spectrum here. Let's draw an ROI over the ionization edge. Go back to the least squares fitting palette, and then we're going to choose in the kind of the fit model type, we're going to choose reference. And that's going to be okay. And then say, what do you want to use? So we want to use that cross-section model that we just grabbed there. Hit OK again. Okay, so you can see now I've kind of introduced some errors here. And the reason that is the cross-section shape, as we know, doesn't, the basic cross-section doesn't really do white lines very well at all. So that's why the kind of the fit has become bad. So one thing that I have kind of already switched on, I switched on this total fit. So if you, in your software, you don't have total fit here, the way that we switch that on is to go up to the options in the least squares fitting palette. And then in the least square fit setup, you've got in live display, total fit should be checked. So you see how that kind of appears and disappears. So we want total fit on. We could also have residual on if we wanted, and that can be helpful. So these two together are quite useful. One other thing that is important here for this example, the combined fit here gives the best result. So we want to use combined fit. So we select OK. So what we now need to do is deal with the white lines. So the way that we can do that is we can just, I'm going to fit Gaussians to the white lines. Just to make it easier, you need to first of all move this ROI off the white lines, because you need to draw new ROIs for the white lines. So let's draw a ROI over the M4. Then go back to the least squares fitting palette, Gaussian, and then, so I'd like to name these because otherwise you're going to end up with a load of fit results and you won't necessarily know which one is which. So let's go up to the least squares fitting palette and then rename this one. Rename selected NLLS fit model. And then we can call that one M4. We could, if we wanted to, we could also keep Gaussian in the name, but I'm going to leave that out. Then let's do the same for the other Gaussian or the other white line. So back to the least squares fitting palette, Gaussian, and rename that one to M5. Then the last thing that we want to do is just bring that back to the beginning, the onset energy of the ionization edge. And that's it. So we have now the background, basic edge shape, and the two white lines taken care of in this fit. So the final thing to do is to just move around. Remember just to verify that fit doesn't go crazy and do anything stupid. So I first of all like to do that with a few pixels in the spectrum image summed. And then finally just go down to something that is our kind of our poorest signal to noise ratio condition. So a single pixel, and just make sure that the fit is still good. It's also a good idea when you do, because we're going to ultimately measure the white line ratio, just get a feeling for when that fit just stops working completely. So there's a point where the white lines completely disappear because we don't have any more cerium. And we probably shouldn't be doing fitting there. So you can see very clearly from the spectrum image where that is, and it's kind of around there. Okay, so fit looks pretty good with these fit components and these windows. So let's go ahead and press map. So I just go back to the least squares fitting, hit map, and hit OK. That all looks fine. So software does the fit for us. So yeah, for this example, I was interested in the white line ratio. So the white line ratio is kind of indicative of the oxidation state of the cerium. So the white line ratio is just the M4 intensity divided by the M5 intensity. So it will be the amplitude of M4 and divided by the amplitude of M5. So the way that we can map that out really easily is to use the simple math. So we just select these two, M4, M5 amplitude, go to analysis, nope, process. So the process menu, you want to go to simple math right at the bottom. And then we want to divide the M4 amplitude. So that is, in my case, it's Q. So amplitude M4 divided by amplitude M5. And it's A divided by B. So it's this one divided by this one. Hit OK. See, we've got some crazy numbers here because we're dividing kind of probably through by 0. So we could have a cleaner script where we don't do that, but just as a kind of a quick and easy demo, it's quite clear where you can ignore the data. So we basically trust our result to about here. Okay, so again, so that we can see where we are on that line, we go back to the fit. We can use the picker tool. So I selected that NLLS fit, use the picker tool, and then that'll extract a spectrum. So let's put that there, but I'm just interested in where I'm on this line. So select your kind of fit, go to SI, mirror extraction ROI. Now I want to mirror to that ratio line profile that I just did. So I can see from on my system that it's image X. So you'll just need to verify on your own systems what it is. So let's go to X, hit OK. Perfect. So you can see where we are on that line. And you can kind of see, if we look here, you can see where the interface is because you can see where the white lines end in that in the fit here. And then if we go out into the bulk, you can see that there's a trend of a decrease in this white line ratio as we're at the interface. So yeah, that's pretty much all I wanted to show you in this example. So the take-home really message is that if you want to do something like this, kind of a hybrid fit where you use parameterized functions plus a fixed reference like in MLLS, the way to do that is in MLLS to use this one here. So you can do that with multiple fixed references and multiple models. So in this case, we obviously only used one reference, but if you wanted to have more, you're free to add in as many as you need or don't. So that's pretty much it. And I'll leave it there for now.